Hello everybody, this is going to be a lesson for chapter 3 on mass relationships in chemical reactions, specifically mole ratios, molar mass, and everything you need to know about stoichiometry, which is going to be one of the more exciting topics for chemistry. Now, before we start, let me mention that stoichiometry is a great way to identify quantities of a substance using chemical formulas and chemical reactions. Now, in chemistry, one of the greatest things about using stoichiometry is that you're able to determine the identity of different substances based off the quantities that are being produced, and also by using mass from a product and mass from a reactant to be able to predict what you're going to get. And that's the reason why mass relationships are very important, because you're dealing with a product and also a reactant and calculating that in many different capacities. So let's talk about the micro world of atoms and molecules real quick. In the macro world, you are weighing objects, so there's no way to really count atoms directly because it obviously is very small. So whenever we interact with chemicals, we always have to weigh things. And then we have to use some sort of representation to count how many atoms or molecules we have by looking at the terminology of atoms and molecules in the micro world. The atomic mass is a great example of something that we could use to identify atoms. So for example, if I want to know what type of carbon I have, or what element I have, such as carbon, I would have to use the atomic mass, also called the atomic mass units, or AMU. Now, generally speaking, by definition, one atom weighs 12 AMU. So basically what they use is the 12 AMU for the atomic mass to tell you that every atom weighs 12 AMU rather than a gram. On this scale, it's very similar to 1 gram is equal to 1.008 AMU or 16.00 AMU. So if you think of atoms as a way, you're looking at atomic mass units for atomic mass. Now let's talk about an example like lithium. So lithium exists as an isotope, basically meaning that you can find different forms of lithium. And so there is, in nature, there's a 7.42% composition of lithium out there, and of the 6.015 atomic mass units. While for the lithium-7, that has 7.016. That's 92%. So most likely you'll find lithium-7 in the world. In the periodic table, they actually account for both of these using what they call the average atomic mass of lithium. And that's the reason why the masses are, generally speaking, not whole numbers, because if you actually average them out by the percentages, the mass that you get from there is actually going to be 6.941, accounting for the percentage. So what you would do is multiply the percentage of what you get for lithium-6 and add it what you get for the percentage for lithium-7 and divide it by 100, which gives you the actual average mass of that. Now here's an example of this. In the periodic table, you do get lithium here at 6.941. So if you're wondered how you get these numbers, it's because these isotopes exist. So again, there's different forms of these elements that are in there. Now we like to call it the atomic mass because, again, it has to do with the atomic mass unit at the atomic level versus on a mass level. Now we tend to kind of sometimes use these in grams, which they are obviously, and then we calculate those on a calculator. So the average atomic mass for lithium is 6.941, and that's a way to represent the mass of these atoms. Now let's talk about another way of representing these same relationships but using a different type of unit. If you think of a dozen eggs such as 12 and a pair of shoes as 2, these are examples of how you can say the exact same thing without having to say I have 12 eggs. You just say a dozen or a pair. So a mole is basically the exact same thing. The difference is that we're trying to represent a bunch of different atoms in exactly a certain area. So a mole, by definition, is the amount of a substance that contains as many elementary entities as there are atoms in exactly 12 grams of carbon-12. So for example, 1 mole of sodium of Na equals to 6.02 times 10 to the 23rd. So if I give you 1 mole of carbon, that equals to 6.022 times 10 to the 23 atoms of that, which is a huge amount of molecules. Now, obviously, we don't use that because it's too big. This is called Avogadro's number, or in this case, 6.02 times 10 to the 23rd. Now, molar mass is the mass of 1 mole of eggs in grams. And so when we're looking at the molar mass, or shoes in grams, or marbles in grams, or atoms in grams, we take a look at this relationship. So we say 1 mole is equal to 12 carbon 12's 6.022 times 10 to the 23rd, which is equal to 12 grams, and 1 carbon 12 atom is equal to 12 AMU. You're pretty much almost saying the exact same thing. Now, obviously, we're using different terminologies, but the idea is still the same. 1 mole of carbon 12 is equal to 12 grams of carbon 12. So if you use the ratios, what you're really saying is that 1 mole of lithium atoms is equal to 6.941 of lithium. And that's the reason why when we use our mole ratios, we always use saying that that is 1 mole of something is equal to 69 grams of lithium. So for any element, the atomic mass unit is equal to the molar mass, or the grams. So if you kind of use these conversions, you can kind of go ahead and make that claim that the atomic mass unit is equal to the molar mass. However, you have to understand that for every 1 mole of atoms, that's also equal to 12 grams. Okay, so here's an example of compounds where all have 1 mole. So 1 mole of carbon, 1 mole of sulfur, 1 mole of iron. If you actually add them up and you're getting 12 grams of carbon, that's what you're going to get. You also get 1 mole of sulfur, mercury, and copper. So if I keep on adding this, I can say, well, I got 24 grams of carbon, or I can say I got 2 moles of carbon. So here's an example. 1 atom to 12 AMU. If you multiply that out by 12 grams of carbon, what you're going to end up with is 1.66 times 10. So I want to do the conversion here from atoms to grams. I'm going to use the AMU example to cancel out the AMUs and end up with the grams. Now, if you cancel out the atoms, you should end up with M. So what we're going to solidify here is that 1 AMU is equal to 6.02 times 10 to the 23rd power. And that's going to give us this relationship. So the relationship between the mass of an atom, mass of the moles, and number of atoms can always go in the middle with the moles. If I give you the mass of something, I would always have to go to moles first, change that, and then go to atoms, and I can always reverse back with only using the moles in the middle. So the molar mass is equal to the gram over the mole of any substance. And Na is going to equal to Avogadro's number. All right, let's take a look if you understand molar mass. So how many atoms are in 0.551 grams of potassium? So in this specific case, I'm trying to figure out and count how many atoms are in there. But in order to do that, I have to figure out what the relationship is between moles and grams. So in order to do that, we're going to make this assumption that 1 mole of potassium is 39.110 grams of potassium. That's from the periodic table. And if we also say 1 mole of potassium is equal to also 6.022 times 1023 atoms, then what we do know is that we can actually convert grams to atoms by using our mole ratio. So I want to convert 0.551 grams. We divide it by that. Then we go into moles now. And then I can go ahead and use another ratio, which I indicate is this one, by 6.022, and I go ahead and cancel out the grams, cancel out the moles, and I should end up with 8.49 times 10 to the 21st atoms of potassium. That means in only half a gram of potassium, I have 8.49 times 10 to the 21st atoms, which is huge. Now, molecular mass. Okay, so I'm going to go ahead and do part 2 right now, so thank you very much for that.